This presentation deals with the self-compacting concrete. I will present an overview of this concrete, its constituent materials, and the key points about its design. Self-compacting concrete is not new. Highly specialized, expensive, and difficult to control mix, even for underwater placement, were produced for a very long time. However, it was not until the late 80s that the advances in admixtures allowed us to increase the fluidity of the fresh concrete to make it self-compacting, maintaining the cohesion for avoiding the segregation. The key aspects of the self-compacting concrete are the following: filling ability of the fresh mix to flow under its own weight and completely fill all the spaces in the formworm. The filling ability also governs the self-compaction. Passing ability of the fresh mix to flow through confined and constricted spaces, narrow openings, and between reinforcements. Passing ability is linked with the filling ability. Both filling ability and passing ability are required for a fresh mix to be adequately self-compacting concrete. Segregation resistance of the fresh mix to maintain its original distribution of constituent materials during transport, placing, and compaction. Additional aspects of the self-compacting concrete are the following: pumpability. Practically all fresh self-compacting concrete are pumpable. Finishability. Self-compacting concrete provides a self-use production of distinct type of surface finish. Each type of finishing requires its own requirements of mix design and fresh state behavior. Self-leveling, that is important for construction of floor, slabs, and pavements. Flow rate, to control the speed of the flow. The flow is important for large or complicated pouring and also in precasting. And finally, washout resistance. This is a key aspect for underwater concrete. A very brief history of the self-compacting concrete. The post-war reconstruction of Japan in 50s and 60s leads to a building boom, being the speed of the construction and low quality the main cause of the deterioration 1 or 2 decades after. Professor Okamura from the Tokyo University, in collaboration with Maekawa, Osawa, and Ouchi, conclude that there was insufficient compaction in many of the buildings that showed durability problems. They received the task to design the modern self-compacting concrete for avoiding these problems in the early of the 1990s. After that, in 1992, there was the first presentation about self-compacting concrete in an American Concrete Institute meeting. In 1997, it was created the first Railing Committee on Self-Compacting Concrete. In 2002, the European Federation of Specialist Construction Chemical and Concrete System published the first European guideline for self-compacting concrete. We have here some pioneering application of self-compacting concrete. In 1992, the foundation and massive cable anchorage of the Akashikai-Kyo suspension bridge were built. A total of 500,000 cubic meters of self-compacting concrete were cast, and the reduction of the terms was 6 months. In 1997, a liquid natural gas tank for the Osaka Gas Company was constructed using self-compacting concrete. The pace of casting was 225 cubic meters per hour, and the reduction terms was 4 months in a project of 22 months. This is a picture of the Akashikai-Kyo suspension bridge with a span of 1,990 meters. The cables are anchored into massive blocks of self-compacting concrete. This is a picture of the Ronda Hispanidad Bridge in Zaragoza, Spain. The inner of the steel arch was filled with 300 meters of self-compacting concrete cast in 5 hours. The span of the arc is 120 meters. The main differences between vibrated concrete and self-compacting concrete are the following: different rheology during casting, but not very different behavior in hardened state. more dense microstructure and fast aggregate interface for the same water binding region. Lower permeability to gas and chloride as a consequence of the closer microstructure of the cement paste. Better bonding between rebar and concrete. Higher sensibility to the curing process due to the higher content of cement and additions. Lower modulus of elasticity for equal compressive strength. And higher autogeneous skin rates, also due to the higher contents on cement and additions. The constituent material of self-compacting concrete. Cement, typical cement, Portland cements are or equivalent may be used in combination with at least one addition. Aggregates, round and crossed aggregates may be used. Maximum size lower than 20 mm and 12 or 16 mm are recommended. It's very important to control the water content in this material. Additions, high content of particles that size lower to 0.125 mm included cement are essential. It is suitable that 70% of the finished particles pass through the 0.063 mm sieve. Admixtures, superplasticities are essential. In addition, viscosity modifying admixture in combination with superplasticity can improve the stability of the self-compacting concrete. The compatibility of the admixture should be checked. Range of the key proportion of the self-compacting concrete. Cement, 200 to 450 kg per cubic meter of concrete. Padware, cement, addition and sand power, from 308 to 600 kg per cubic meter of concrete. Paste, power plus water, 33 to 40% of the total volume of concrete. Coarse aggregate, 750 to 920 kg per cubic meter of concrete. Fine aggregates, 700 to 900 kg per cubic meter of concrete. Water, 150 to 200 kg per cubic meter of concrete. And additives as needed, typical values range from 1 to 2.5 cement weight. We have here some examples of the use of the self-compacting concrete. This is the Guardian del Castillo Bridge in Alcalá de Guadaira, Spain, with very narrow passing zones among rebars for concrete and curved surface. This is a general view of the finished bridge. It is worth noting the quality of the dragon tail with a problematic for forecasting. This is the Oscar Domínguez Museum Wall in Santa Cruz, Tenerife, Spain. I would like to highlight the difficulties to avoid voids during casting under the expanding polystyrene pieces and the good quality surface of the finished wall. In this case, we have a photo of the Jerónimos Cloister in the Prado Museum in Madrid. Colored, self-compacting concrete was used for the walls with a high quality of architectonic concrete. Thank you very much for your kind attention.